Right, let's get started again. So before we switch over to the talk, I just want to, on the behalf of all the organizers, I wanted to thank everybody who attended the workshop and spoke at the workshop. Also, I want to acknowledge there's 3 organizers who, for various reasons, could not be here, and so they are Nathaniel Fialkov, Sandra Zilis, and Alexandra Silva. And in fact, it was originally their idea to try to create a program like this. And so I want to acknowledge all the work that they did. And along with Marcell and me, I think we've had a lot of fun putting this together. And I want to thank you all for being here and speaking. All right, with that, I will turn it over to Sebastian.
And maybe also before we continue, let's also thank the speaker, the organizers then for their efforts in bringing us all together here.
And last but not the least, I want to thank the Simons Institute for hosting this, and Omid over there for helping us with all the AV. All right, now really over to Sebastian.
Now I don't want to thank anyone right now. I want to introduce Marcell. Marcell did a PhD in Sanjit's group while I was a postdoc here, so we've known each other quite well. He's done tremendous work in the area of learning specifications from behavior that the policy is doing, right? So it's the inverse kind of problem. And Marcell has a very bright mind. He's constantly connecting areas that I had a hard time following sometimes. But his creativity has really shown up in his work, and how he couldn't overcome difficulties by connecting different areas. So I'm super excited that he will teach us a little bit about learning automata by demonstrating some nice graphics or something.
Thank you, Sebastian, for the kind words. Yeah, I was joking in the other, I think yesterday, that the last time I had a Simons talk was my daughter was, I think, about 3 or 4 months, and my son is about 3 months. And so if I make any mistakes today, or fail to include there wasn't out of malice, but out of sleep deprivation. All right, so I will go ahead and get started. Yeah, so we're nearing the end of the Simons Institute this session, and I wanted to kind of give the premises of my talk, and some of them are building off of things that we've seen throughout the week. And so the key premise of this is that unambiguously and formally specifying goals or tasks or objectives is helpful for trustworthy AI. At this point, I'm just going to take it as axiomatic. Bayezid, Amish, and several others gave some version of this argument. But the quiet part that I wanted to say out loud right now is that almost nobody actually gives you any specifications. And so this is always this tension in formal methods and verification, where you want to prove something, but that's where it stops. You want to prove something. And you need to at some point write down what you're trying to make the system actually do. And it's easy maybe to have the terminal goals in mind, but in order to say something useful, you often have to have a very well-defined specification of what the task should be. And so that's very much the goal of this talk. So what I'm going to get at is 3 areas. I'm going to start with learning automata from demonstrations. So this is without language. We'll introduce language later. Then we're going to talk about learning automata from demonstrations with language. So we're going to introduce the natural language. And then we'll talk about teaching automata via demonstrations. And I'm using automata here very much as a stand-in for just a general formal specification. I have many reasons that we can talk offline why I pick automata, and I'll have some of them in this talk. And much of the work actually extends to different classes of specifications that just have Boolean semantics. Okay. And a key theme that we'll be using throughout this talk is to kind of observe that using labeled examples, we're able to fuse information across modalities. And this is going to be a key trick that we'll use, and I'll come back to this again. But this is just something to keep in mind throughout the talk. All right, so I'm going to start off with a motivating example. So consider an agent acting in the following stochastic grid world. So what you see here are different colored tiles and a path. And we're going to assume that the agent has 4 types of actions. They can move up, down, left, or right. With some probability, it's a windy day, they can slip and they'll maybe transition stochastically. So they may try to go left but actually go down. And the question that we're going to pose in this talk is, what is the agent trying to do? Right? And so if we kind of sit and kind of walk through this together, we might think, well, this path is very biased to reaching the yellow tile, so maybe that's what they're trying to do. And then you maybe think a little bit more and you say, well, if that were all, this counterfactual, this path would be kind of surprising, because why are they going all the way out of the way to go visit that brown tile? And then you may think, well, why didn't they just take the shortcut through, past these red tiles? And so somehow, whatever explanation that we give needs to account for these various, aspects of the task. And so the key point that I'm trying to illustrate is that there's a lot of information, even from a single incomplete demonstration. Note that the demonstration never actually reached the yellow tile. I just made that inference without actually having it. So this isn't a positive example. If I were to have a specification saying, go visit the yellow tile, you can't label this as positive. But still, we kind of guess that they're maybe going to the yellow tile. And the motivation for this is inspired by a number of works. So the idea for communicating through actions, it's essential for interpreting other signals. So we can talk about language, disengagements, other agents. And actions are incredibly diagnostic. This is something that was very inspired by Anka Dragon's work when she first came to Berkeley, is this idea of like, if I'm going to pick up this cup or this remote, I can exaggerate my motion. And by doing so, you're able to quickly infer that this was actually my intended target. Right? So actions have this power that is often useful in addition to or even without language. And so then we come to the question of how should we represent the tasks? And the desired properties that I like, yeah.
So can you go back? I think with the demonstrations that you're looking at, right? You're not just looking at what the intended action was, but also what the actual outcome of that action was.
Yes. Yes.
But I can immediately see how you can observe what the outcome of your action is, right? With your arm.
Yeah.
But I cannot necessarily see what you tried to tell your arm when you were making that.
When I made my, yeah. I think it's a good point. I'll largely sweep under the rug through this talk. The formal way that you make this happen is you can integrate now over your belief over what the actions were. I think it's the simplest model. Yeah. So if you have a model that marginalizes easily, then either by sampling or by be explicitly, you can always do that trick.
Yeah. Okay. But in your grid world example, you're basically like, there's no way once you're integrating that you can see that you try to not reach the water, right? The blue tiles. I'm inferring that they're water.
Yeah. That example is there's not enough high resolution. Okay. So that kind of setting would be something like this is a more actual robot task, and so you can see like a slippage. You see the tires move or something like that. So you have some other signal. Yeah, this is very much a simplifying cartoon so that we can But thank you. Yeah, that's a very good clarifying point. All right. So some properties from the task representation that we maybe would want. I'm going to argue that it's useful to decouple the task from the dynamics. This is something that we saw Amish make the point of yesterday, that when you have this, when you have the specification, it's useful that it's a binary signal. It doesn't really matter what the probability of the slipping was. We're going to prefer sparse rewards in order to do that, and we're going to also want to have the ability to describe temporal tasks. And finally, we're going to want to have support composition. And the example that I always like to give for wanting to be dynamics invariance comes from our NeurOps 2018 paper, where you consider you have this Markovian realization of rewards, trying to get the agent to avoid the red tiles while going to the yellow tile, right? And if you just slightly change the reward signal, now the agent, the optimal policy wants to lead the agent to the yellow tile. And so we have to have this notion of a common currency in order to say how much does avoiding yellow affect going to yellow affect avoiding red. And we're just going to bypass the whole problem by having a Boolean sparse semantics. And the key question that we want to kind of get at is, in order to separate these things, we have to have a notion of memory, that once you reach the red tile, it was impossible to actually satisfy the task. And so then we ask, what memory is actually important? That's a question we're going to keep coming back to. But first, we'll postpone that and we'll ask you, how do we represent this task? So again, I'm focusing on tasks as Boolean specifications. So we're going to be using the set-based semantics. So any path that you see, we're thinking of it as a point in some higher order set. And we're going to say that it satisfies the specification if it belongs to that set. So automata, logic will all kind of follow this structure. And then our objective is this sparse indicator. We just want to sample something that's belonging to that set. So very similar to what we've seen already. And of course, we can derive these by automata, and I'm going to largely stick to automata. And we're going to call a collection of these task specifications a concept class. So to connect it to some of the learning theory. And so our goal is to kind of search this large space of concepts, and it's kind of a needle in a haystack problem, looking for the one that's explanatory. And what's nice about the sparse semantics is they immediately give you incremental learning, right? So one thing that I want to focus on here is that we're not super interested in learning very complicated tasks, because we have the ability to learn things one at a time. If I am demonstrating to you a task, I can tell you or have previously shown you this eventually recharge and avoid lava, and then I can ask, what is this third task that I'm now trying to add, given that you already know those two things? And so we're able to kind of construct our concept class compositionally this way. So restrict to things that already have their intersections with these sets. Okay. And this is the automata that would then add the don't recharge while wet rule that you were seeing. And the reason that I'm focusing on automata is, in some sense, they're the simplest structure that you can get that explicitly encodes memory, right? From like a formal learning perspective, you've got Noether's theorem, Myhill-Néraud, which tells you that these are the resulting quotients of the residual languages. Like you couldn't get away with having less memory. So this is like the minimum amount of memory that you need, and we're going to use that as our justification for why we can explore this. So those are the desired properties. That's why we're focusing on automata. And now I'm going to get into actually how do we try to learn these tasks from demonstrations, get into the math of this. And the recipe that we're going to go through, we're going to take a Bayesian approach. We're going to want to be able to compute this posterior belief. So we're going to assume, and we'll talk about later how we can get one, a prior over the automata, and then we will have a likelihood function of the given path, given the automata. And then we're going to come up with a search procedure that, given that posterior model, enables us to search the space and find likely candidates. And so very much this is a search problem where we're going to rank and we're going to find the things that we think are explanatory. Okay. So how are we going to argue that we should compute this posterior belief? And the goal or the idea is to frame this as inverse reinforcement learning. So there's a large literature on inverse RL where you have a Markov decision process. So your next state depends on your previous state and the action that you took in your dynamics. So this is like in the grid world, what cell you're in and what action you took. You have some slip probability. It's not necessarily deterministic, but it's generally this model. And we're trying to maximize the expected reward of the state. Of course, we have to augment our state in order to code an automata, but we're just going to kind of ignore that for a second. This is, there's the maxent RL problem. And we're going to, assume that the agent is producing some kind of stochastic policy and they're to optimize this reward. And so the inverse RL problem asks, given a series of demonstrations, what reward best explains the behavior? And immediately if you sit and think about this, you realize that there's no unique explanatory reward. The all zeros reward works. Any constant reward is also just as explanatory because it's a constant max, right? So there's no real or you could overfit to the demonstrations and like have literally only the demonstrations are possible. So there's many ways to fill this in, and so you need some other criteria. And the criteria that we take is this idea of maximum causal entropy, subject to feature statistics. Now, this isn't going to be an information theory lecture, so we'll keep it fairly high, but the general intuition is that we're going to try to match the entropy, so the negative log probability of the action given the state sequence, subject to some expected reward. And the intuition is that we don't want to overcommit to any particular strategy. So what this is going to do is say, look, there's many ways to perform a task. You're not going to have policies. You don't want to induce policies where there's like only one way to do the task if there are multiple. So you're going to try to spread out your belief. And kind of mechanically, what happens is that this is the same thing as saying that we have this kind of Boltzmann rational model. So that the likelihood that the agent's going to wake up in the morning and use policy, policy 1 or whatever, is going to be exponential in its expected reward. Right. So that's kind of the model you should think. So good policies are much more likely than bad policies, but other than that, you don't really know. And formally, what's nice about this particular formulation, and Brian Ziebart proves this in his thesis, that this minimizes the worst case excess bits you need to encode the episode. So if you were to watch the episode and you imagine that you're writing this down and communicating it to your friend over a text message, and you get charged every single time that you send a bit, and it's evolving over time. You want to kind of minimize how much you have to spend. So that's the general idea. You want to be robust to under these assumptions. Okay, so our reward is what should it be? We again said that our satisfaction is a sparse objective, and so of course we're going to use this indicator. And so we have this 0, 1 behavior. So if the episode, if you accept the trace, then you're going to have 1. Otherwise, you'll have 0. And the expected reward then ends up being the satisfaction probability. So, a quick aside here, I don't have it on the slide, but it doesn't actually matter what these two values are. You could have A and B, as long as they're not the same, you'll end up with the same results that we have here. So it's a fairly straightforward proof. But the indicator is nice because you get probabilities. Okay, so this is the model that we're going to use to assign to likelihoods. And what's nice, another theorem that you can find in this literature is that exponential belief corresponds to this soft Bellman backup. So the negative log probability of the action given your state sequence is going to be this soft Q value minus this state value aggregation. And the value of the action, the value of the final sequence is either 0 or 1. We'll come back to this later. But that's the general idea, is that you should think that this can be mapped to some variant of Q learning, where the log is telling you the probability. And so therefore, this is a softmax distribution. Okay. Okay, so taking a step back, reward learning offers a lot of ways we could have done this for ranking specifications. Inverse optimal control we could have taken. So we could have just taken this perspective of you're just trying to optimize. We could have taken a more Bayesian approach, or we're focusing on this maximum entropy inverse reinforcement learning setting. But again, the key question from my perspective of learning automata is like, what memory does the demonstration actually imply that you should be looking at? And this is really the key question. We could have come up with lots of different formulations of this. We would have ended up with slightly different variants of the theory, but you have to answer this question. And of course, the problem is that we don't have a gradient to guide the search over this discrete structure, right? So in the reward setting, we would have just optimized some gradient. And prior to this work, the literature really focused on this naive syntactic search, and I'm guilty of this as well. So here's our 2018 paper, and we defined this search over a grammar. So what we did is we looked at the problem. We kind of already knew what the answer we wanted to look like was. We came up with a grammar that fit that, and then also included a bunch of other things. And then we said, see, we could find it. But this is very unsatisfying to me. And it has this issue where you're conflating this inductive bias with search efficiency. So whenever you put down a grammar, you really have to argue that this is the grammar. And when we get to teaching, this is going to be even worse, because we're going to be modeling the model of another person. And so I don't get to tell you what grammar Sebastian is using for his inference. We just have to deal with the one that he has. And so we need something that is not super biased. And so when teaching, this is even harder to justify. And we wanted a general strategy that works with less structured concept classes. So we want to kind of relativize this to a learning oracle. And most importantly, this search ignores the demonstrations. So we want to somehow use all that information that we talked about in the initial analysis to find the specification. And so when we come back to this question of what memory, the argument that I'm going to make is that we need enough memory to separate these counterfactuals. So when we did this this kind of ad hoc analysis, we decided that maybe these are good, this is probably bad because you didn't do it. We need enough memory that we can separate them. And at that point, it starts looking a lot like a passive learning system. So we'll come back to that. And in particular, we're going to describe this loop where we're going to sample candidate tasks. We're going to have this fancy surprise guided sampler. It's going to be where most of the math lives. And that's going to give us a counterfactual labeled path. For example, if you're going to yellow, if that was our candidate task, it's surprising that you didn't take the shortcut. So that's probably a bad path. And we're going to come up with a principled way to make those kind of guesses. We're going to have this example buffer, which kind of holds these, maybe drops them when we think that they're no longer relevant, and then repeats the process. And so this will be our search scheme. Yeah, is there a question? Yep.
Right. So it's regarding the state representation that is available. I don't know to whom, because there seems to be a separation of you as a designer versus the agent.
Yeah, so the agent has knowledge of their task in entirety. But we, as you kind of are alluding to, have this annoying problem that we can't just augment the state space with the task. It'd be untenable. You can't do it with Automata, for example. So yeah, we're very much in the setting where we see the projection of without the task of what their state space must be. And we're guessing, in some sense, what is the necessary memory in order to model.
Right. So the agent really is operating in a more complex system, but you see a projection down to an MDP essentially.
Yes.
But the agent is not having a policy in this MDP because it's doing some task.
Yes, exactly.
All right, thanks.
I think for the
I also have a short question. All the examples are based of the same policy, right? So you're having a policy once and then you're sampling.
Yeah. So there is an extension, and I'm happy to talk about it offline, that you can do that to make it work with multiple policies. In some sense, I'm going to show a prefix tree later, and effectively you need it to be separate prefix trees. But yes, for simplicity, let's assume that it's one demonstrator. And maybe one thing also I didn't specify, make explicit, is that the examples that we have here, when I say example, I mean a sequence of like colors in this situation, the labeled predicates of the automata. And when I say paths or demonstrations, I mean state action pairs. And so that loop that I was just showing, the way that I like to think about this is what you've done is you've transformed the problem into a walkthrough labeled example space, where each of your labeled examples is now going to induce another concept class, and you're going to sample this concept class, the subclass for candidates, and just like with version-based learning, that candidate is maybe going to then restrict the future examples that you have, which then restrict the concept class. And so this is kind of guiding a search and focusing on the relevant details. All right, so I'm going to focus on this surprise guided sampler, and in particular, the number of nats or bits up to a constant, they're the same thing, to describe the demonstrations, assuming our specification V. And if you write this down, this is the negative log probability of the demonstration, or this path, given our specification and our dynamics. So we're just going to hand wave away the dynamics are. But what we're interested in is to see that this function is going to factor through some RD, really. And we're gonna have this proxy space that we will actually do our derivatives through. We can't differentiate in this space; it's too discrete. It's untenable. But we're gonna find a proxy for this that we then guides our search. And then we're gonna try to pull back those changes prescribed by the gradient and tell us how we should update. Okay. So the first key idea is to kind of reframe the problem as choices along the demonstration. So if I have this path here, you can think about, I had the sequence of state, and then I had my action, state, action, state, action, state, action. And there's many ways to deviate from the demonstration, right? So there's many different ways that I could have done this. And when I talked about this, this distribution that's actually going to determine that, we said that, we have this Q value function. And now is where I have to actually go into the details of that. So, we have this policy where our Q functions are defined via this soft Bellman backup. So we have the Q function is the expectation of the value function given the state action, the state sequence up to now and the action, and the value is either the log sum of exponentials of the Q function if you haven't finished the episode. Otherwise, it's some lambda of the it's lambda times the indicator, right? And in order to find the maximum causal entropy policy, what you do is you tune lambda in order to match the satisfaction probability, right? And again, yeah, so it's often helpful to view this this log sum of exponentials as like a smooth maximum. And what's nice is, these deviation values are summarized actually by this value in Q. So you've got this, you have Q and V there. The key detail to note is that the expectation and the smooth maximums are associative and commutative, right? So just algebraically, we can forget what they actually are. We just say, okay, they're associative, commutative. That means that I can group the actions and their values, and I can say, actually, deviation by itself has this value, right? Because I could decide how I want to split that. I can first decide what that value is, and then I can split it up. And so what's nice is we get to summarize all of these counterfactuals at this state via a single action, just deviate. From our perspective, we'll never look past that. And so then you can reframe the policy as, what's the probability of conforming? So, given that I've seen this prefix, what's the probability that I'll conform, this white label? And now it's a softmax over these two options. And what's nice is independent of the number of actions in the state, and we'll come back to that in a bit. It's going to be useful to think about how we might extend this to deep learning or a black box setting. You only need the transition probabilities of the demonstrations, and I'll make this more explicit here in a second. But this is the key idea. This is why we're doing this. All right. And the second observation is that we can view the demonstration itself as a computation tree. So if I look at this path and I flip around the edges, in order to compute, the environment nodes are the things that are doing these expectations, and the agent nodes where you're making these decisions are doing these smooth maximums. They're computing the Q functions. And so I have this computation graph, which then determines the innermost Q and V values, right? And so how surprised we are by this demonstration, given our specification, which then induces a policy, is entirely determined by these values of pivoting. And I'll describe what I mean here in a second. So the idea is, if you've got some path, and this in general, this isn't if it's multiple demonstrations, this will be a tree. The probability that you would deviate is entirely determined by the value of deviation on all these leaves, and then the final values of the actions. Yeah. So this value is, in some sense, summarizing all of the different ways we could have completed the demonstration. And so the surprise factors through these ways that we can, as a function through these values. So we have this new function here, this determined by the prefix tree. And what's nice, and what I prove in my dissertation, is that if you kind of mechanically walk through this, you find that the gradient with respect to the k value here, is what we call the pivot values, is entirely determined by the transition probabilities of going from node I to k in this graph, right? So if I'm at node I here in the graph, and I'm interested in how much it would change if I change this value, I can look at that value versus it's the sequential one. So if this was I, this is j, what's the difference in probability? So how much did we change probability by doing this action? And that determines everything. It's a nice trick. And so then we have this third idea of okay, well, how are we going to actually use this? And so we introduce this third idea of toggling the trace labels to manipulate these values. So I'll kind of explain what I mean. So again, we have this idea that every pivot subtree is summarized by some value. And if I pick some path through there, it has some label that's given by the specification, right? So I took some counterfactual path, ended up here at the leaf, and this was bad. So we give it label 0. If I flip the value, you can, it's not super hard to show because these are monotonic functions, expectation and smooth max, that the value must have increased, right? And so, and furthermore, you can show that if you sample from the policy, the things that were likely given that label are the things that are going to affect this value the most. And that immediately gives us kind of an idea. So what we'll do is, you imagine that you have this likely negative path. If you were to deviate here, then you would have maybe gone this other action. So we were thinking, okay, well, we could have done this action, but we could have also taken this counterfactual path. It's pretty likely to pivot at the beginning. And so we say, okay, this is currently labeled positively under the hypothesis that we're going to yellow, and we're going to mark it negative. Right, so that's the essence of the trick. And this gives us this idea of a surprise guided sampler. So we have these this kind of recipe where you find a candidate specification, we compute that proxy gradient. We define this this distribution over the nodes in the tree where we're going to pivot, or where we're going to deviate from the specification, from the demonstrations via the softmax in the gradient. And then we're going to sample a path conditioned on that pivot. So we're going to pivot at this particular point using the policy. So we're going to use the same policy that the agent was using, but we're going to assume that the label that policy will have is in the same, is labeled the same way that the gradient is, right? So that is to say, if we want to decrease this value, or if we want to, if the gradient says that the surprise would increase if you were to increase that value, you select, which would correspond to this becomes more valuable of a path. You then select, you sample this kind of a path, and which is positive, and you flip it to negative, and you just kind of repeat. And yeah, so you give the label by the opposite direction of the gradient. So, take a quick water second break. That's it though. That's the surprise guided sampler. So these other ingredients, they're also important, but I promise that the majority of the math is now, we're going to coming up on that, actually using this stuff. So we have this candidate sampler, and here we're going to say it can be any exact passive learner, right? So we're going to feed it these counterfactual labels that we've been collecting, and then I just want to be able to say what are the candidates that are remaining, what are good candidates still. And so you sample one, and then it'll output your new task specification. And so you can use many such samplers. We have one that we based our software, which is based off SAT solving, because you can enumerate lots of examples and you can maybe sample them according to their size. You can do this with LTL, and I'll show. I have an idea for using natural language with this as well to try to inject it at this layer. Okay, and then this example buffer, the last ingredient here, is essentially simulated annealing. So we tried multiple different ways, but the way that really worked well at the end is simulated annealing. So in the state of the simulated annealer is the set of labeled examples, and its process for being updated is just you sample a new path using this surprise guided sampler. It either rejects or accepts, including that, and then also with some probability it might just drop a label example. And the idea there is that if it's important, it'll probably come back. All right. So this is the idea is we're going to run simulated annealing over this process, and we're going to try to optimize this description length. So the idea is the likelihood minus the prior, and the prior that we're going to use because it's natural and because I have a strong bias towards Salmanoff induction kind of techniques, is we're going to use the description complexity of the automata. So if the automata takes a lot of bits to describe, it's going to have a lower prior. Okay. And again, just to reemphasize this point, what we've derived is this kind of walkthrough labeled example space, where the simulated annealing is kind of telling us how we move up and down in hill climb. Okay. So I'm going to show two experiments, and then we'll see a couple more examples in the teaching section. But just for time, I'll kind of walk through two our motivating examples. So we have this incremental learning using one incomplete unlabeled demonstration. So same setup as we had before. And we're going to give this example, and we're going to give two of the rules, and we're going to try to figure out the third rule. And the second experiment, we're going to give two demonstrations, and that's because it's not enough to learn the. You can try this out yourself, but this wouldn't be enough to learn all the rules because you don't kind of express enough. You end up overfitting to just going to yellow. So we give these two examples where you actually show slipping and then non-slipping behavior, and then we show that that's also enough. Okay, so this is the key plot from that work, and let me kind of focus on the left one here first. So this is the case where we're incremental, so we already have most of the tasks figured out, and we're just trying to guess a few examples. The x-axis here is how many loops, how many effectively counterfactuals we did, and the y-axis here is the energy, which you can remember is like is how likely this is, or in our posterior model. And so the goal is to kind of quickly collapse this. The correct one is about this point. So we want to quickly find the right or explanatory specification. Doesn't have to be the same one, just one that's as good as explaining it as the correct one. And so we quickly collapse to that point after, depending on the temperature of our softmax, so how much we rely on the gradient, we either find it very quickly or it takes a bit. And in the monolithic case, we show a kind of similar result. So we have this initial progress, but you'll notice it doesn't actually get to the end. And so it's still much slower than the incremental case. But ultimately, within like 40, 60, 70 iterations, depending on the temperature tuning, it's able to find it. So we are very excited with that. It's, from a simulated annealing perspective, we know that if you give it enough time, it'll find it. But in practice, it's an open question of how fast it's actually going to go. This is very much best effort. Okay. But yeah, so the most probable DFAs do in fact kind of match the ground truth. We can walk through the settings. So this is in the incremental case, we learned that if we reach this red tile, it's a bad sync state. Otherwise, we have this like recovery condition. If we visit blue, we need to visit brown. Otherwise, we have issues. And the unlabeled demonstrations also recover an interesting case, but because there's no reason to actually include this red sync because the episode ends at that point. And so there's a few different degenerate DFAs that have very similar probability mass. So this one, for example, includes this arrow, which more or less we weren't expecting. Yeah. Okay, so that's learning tasks from demonstrations. I want to now switch to language because usually when you have a task, it's very easy to actually communicate parts of the task. Right, and you don't necessarily want to have to start from scratch every single time. You don't want to, in my example where I gave incremental learning, I, as an expert in formal methods, presumably was able to write down, this is the first task, this is the second task as automatas, and then, be able to work with that. And to make this useful, you kind of want to be able to give that partial information as natural language and then kind of work from there. And so that's the goal of this next work. And so we asked this question of how can we translate these informal requests into these machine checkable objectives? And then we had, ChatGPT and the like came around, and this is something I'd been struggling with my whole PhD, and it's like, well, maybe we have this tool that can actually try to solve this. And so the objective that we're going to do is we're going to try to view this LLM as a membership article, right? So we're going to try to reduce this to actually classic automata learning. And the idea is that we're going to ask the LLM yes, no, and sure questions, right? So rather than asking the LLM to translate it into a Python program, which then, gives me the right language or somehow come up with a DFA, we're just going to say simpler. Is this a good example? Is this a bad example? Or are you kind of unsure about this? And then again, coming back to this this point I made at the beginning, we're going to try to communicate between these modalities using the language of labeled examples. Okay. And so we're going to be able to fuse information between the language and the demonstrations that way. And so the project, we found a cute name for it, LStarLM, an homage to the original LStar algorithm. Regretfully, the LStar backend is actually not as good as our SAT-based one, which is very frustrating when we were writing the paper. I really wanted it to be the best, but still LStarLM we found it too nice of a title to not go. And the idea is that we're going to have this setting. Oh. Of course, she can go to that website and she can see all the information. Of course, I'm glad that it'll make it to her. Okay, so that's my highlight of my week. Hearing that. Okay, so the general architecture is fairly straightforward. We're going to have our labeled examples. This can be an empty set, but for generality, we include the ability to maybe the user already knows some labeled examples. They'll give us some natural language, and they'll give us demonstrations. And of course, the demonstrations are just going to get piped right into this demonstration-informed specification search that I spent the first half of the talk talking about. And the language is going to get mapped to this language model. And then the idea is that this DFA learner is going to act as our kind of intermediate mechanism to kind of fuse that information. If I went back to that previous picture of we had the concept learner, the surprise guide sampler, and the example buffer. This is very much just acting from DIS's perspective as a concept identifier. So we just use the new concept identifier from its perspective. And then from the DFA learner's perspective, this is just providing some kind of side information in terms of these are examples that you should be, you should respect. And so just to give an example prompt, because we're doing language models, the type of thing that we're trying to say is, a robot is operating in a grid world and can visit 4 types of tiles: red, yellow, blue, green. They correspond to lava, recharging, water, drying. And the intuition for this kind of a statement is maybe there's some implicit knowledge and language that maybe you want to use to bias. The robot is visiting tiles according to some set of rules. This will be recorded as a sequence of colors. The rules include the sequence must contain at least 1 yellow tile, i.e. eventually recharge. The sequence must not contain any red tiles, i.e. lava must be avoided at all costs. And a positive example must conform to all the rules. That's the idea. And then, where does the actual membership query happen? It happens here. We say, is the following sequence a positive or a negative example? All right, so. And then please respond yes, no, unsure. And that kind of constrains the distribution so it knows that it's what it's supposed to actually be doing. And so the trick then is, we have this cache of examples every time we do this interaction where we've stored the labeled examples here. So if the LLM is asked this sequence, we don't even bother asking the LLM. We're not interested. This is coming maybe from this. Otherwise, it'll pass through to the language model and ask this kind of question. This is what I was saying with the sleep deprivation. The slides aren't as quite polished at this point, but bear with me. We actually see that using our SAT-based passive learner, we're able to accelerate demonstrations even without explicitly giving the specifications as part of the concept class. This language model is able to kind of extract enough of that information, where the number of iterations, which is supposed to be down here, is competitive with our incremental example before. And if you saw, that's actually the same kind of setting that I gave. I didn't give all the rules. I just gave 2 of the rules, at least in this corner. And then down here, when we show if we give all the rules, it's able to learn even more robustly. Okay. So for time, I'm going to leave that at that. It's maybe like 5 more minutes, right? Yeah, cool. So I'll do teaching. Fortunately, teaching is actually, once you have a lot of this machinery, teaching is a lot more straightforward. I said I'd give some more examples. The idea is that, can we generate pedagogic demonstrations? So I'm going to have this likelihood model that we just talked about before. And can I convince that model to guess the right demonstration? And we're going to use that as a proxy for a human learner or something like that. And so we ran this mechanical Turk study where, or I guess it's on Prolific, but the same idea where we asked humans, you're going to be shown these examples. Can you guess what the rules are? And so for example, here we might have this. So this is a task we've already seen. Maybe we'll do this one. So we have this rule, and if you look at the demonstrations, we have 2 kind of modalities: doing, where we just perform the task either way. So in this particular setting, it doesn't really change. But in this kind of a setting, here, this is a nice one. You're supposed to go to this red area while avoiding yellow. And it's very clear from this kind of over exaggeration of the motion that you kind of want to avoid yellow. And if you touch this blue tile, you need to touch a brown tile before going to red. And so what happens is, the agent tries to come over here, it slips, comes down, has to touch the blue tile, and then it goes through. And we want to generate these kind of pedagogic examples automatically. What's nice, I guess, that I'll highlight is that it did seem to help. So when we were asked, the way that we would test is we would show them the demonstrations, and we would do the same thing we just did with the LLM. We'd ask them yes, no questions. Is this a good example? Is this not a good example? We didn't dare ask them to give us the automata. We didn't think that would work, but we were asking, are they able to guess about rules that examples that they had never seen? And we showed that showing and doing generally helps in situations where they're predicted to be different. So that was fun. And our recipe for generating them was pretty simple. Our task induces description lengths of the demonstrations, and we find likely paths given the ground truth that have a shorter description length than the learned task distribution, and a long description length given the ground truth task. So you're trying to separate those behaviors. And so you do this kind of trajectory optimization. run it through disk. Disk gives you a bunch of things that I said, oh, this seems like it, maybe we're the candidates. And then you try to teach against those. And you just repeat this loop. So that was nice. That ended up working much better than I think I was initially expecting. And so we had this nice method then for teaching using demonstrations. I'd like to end the talk with kind of some summarization. This talk was biased towards these learning contributions. So we talked about learning from unlabeled and incomplete demonstrations at a Markov decision process. We showed that it supported monolithic and incremental learning. We showed that it only needs black box access to a maximum entropy planner and a concept identification scheme. And we also showed that we could generate these pedagogic demonstrations. And very recently, we're now figuring out how we can include natural language descriptions in our identification loop. So then the question is like, what do we want to do next? And what's nice is that there's a clear path to scaling up this mechanism. I only showed you grid world examples, and throughout my PhD, Sanjay would ask me, when are we getting a non-grid world example? And the problem was that we need to estimate this policy on a prefix tree, and I really only knew how to efficiently do that. Because remember, we have to do this every single concept. Like we have to be able to given the concept ahead of time. There's too many, I can't enumerate them ahead of time. This will come up with wild specifications. And you have to then be able to say how likely is something. So this is kind of the bottleneck. And so we need to be able to sample likely paths given that policy. And what's nice is this actually plays really well with the approximation methods. We're just using the black box deviation probabilities. And that surprise sampling that I showed earlier, the gradient was linear in the error of the transition probabilities between those points in the tree. And so if you have a good function approximator, you're only going to grow your error in the gradient linearly. And so we think that this is wide open for the ability to do some type of PPO or function approximation deep learning approach. And in many ways, this was the initial inspiration for this work with Nicholas and Baezi on approximating learning to encode DFAs to send them to these agents. And so one day maybe we'll revisit this. And the other thing that I think has been largely untapped and something that I want to at some point be able to do is learn to do multi-agent assume guarantee reasoning. So Overcooked, which is an example that we saw yesterday, or at least teased yesterday, is this task where you've got a cooking simulator and the different agents have to figure out how they want to split the task. And everybody kind of knows what the task is ahead of time. You're trying to satisfy the orders. But the real question is, if I'm playing with another human or another agent, what assumptions are they making about me? And how can I then synthesize a policy that jointly tries to optimize the policy? And I think that there's a lot of interesting connections with the work that we've done on learning to try to fuse those modalities. And yeah, so maybe a pointer to correlated equilibria as an interesting likelihood model. With that, I'll end. Thank you so much for listening and humoring me. It's been a pleasure. Thanks.
Any questions? So then I'll start with one. This L-star and other active automata learning approaches have been used to learn protocols for SSH, TCP.
Yeah.
And there you can get a natural language specification, which is typically a few pages long, right? It's a standard.
Yeah.
But it would be great if we could use these natural language standards to bias our active automata learning towards this. But it looks, I don't know, because here you had these things with lava, which kind of in my head immediately say avoid, and then if I look at a SSH standard or so, I don't immediately start to understand them. So I'm wondering if you have any thoughts on that.
Yeah. So yeah, like this example here. So we've tried this without disk in the loop. And for small models, this ends up being really important. This kind of corrective feedback, the models hallucinate too much. And we needed a mechanism to have some sort of supervision to actually do a correction. Because at some point, the model starts, you mess up one time and you're yes, no, and sure. And then you generate this like massive example that you didn't go. I know there's work on non-trustworthy, like untrustworthy oracles, which maybe would help. But this was the reason that we kept dis in the loop was for that. It's like I would worry with these very factorized protocols that it may be unstable. And one nice thing with this setting is that we're kind of assuming that we're learning fairly small chunks at a time. Yeah.
Thank you. Any other? Yes.
All right, so I have too many questions, but I hope to find you afterwards. I would just ask one now, which is, during the demonstration, what can you see from the agent, in the sense that, do you see just the state trajectory, or do you see state action trajectory?
Yeah, it's a very good point. And this work, what I'm showing here is all you see state action. The cop-out answer to it is what I gave Sebastian earlier, that you could hope that you can integrate over the actions. And actually, in many of the models that we've looked at, it's not. So what happens in that setting is that you have multiple actions that you're running. You're essentially running so that surprisal gradient formula that you saw earlier, it's going to be linear in each of those models, because given that this was the case, given this is the case, and so you have to integrate that over those situations. What's nice is gradients are linear operators, and so the thought is that if you guess different action hypotheses, you should be able to then have each of their contributions in that gradient. Whether or not that's actually numerically feasible is something we haven't tried, but it's the type of thing that I think is really interesting. Something I also haven't mentioned that we've been hoping to look into is actually learning how DIS is guessing, how the sprites guided sampler is actually doing this process, because then you can imagine that in a simulated environment, you learn this process where you do have the actions, then you kind of do function fitting to then try to approximate in the case you don't. But it's 100% a valid concern.
If not, then let's go for lunch, and we'll reconvene for the afternoon session at 2 o'clock.